Every single piece of data crossing a local network segment is precisely directed by a 48-bit hexadecimal string. IT professionals often categorize the Media Access Control, or MAC address, as a static hardware serial number, a simple tracking tag for a physical interface. The EUI 48 standard operates as a dynamic routing primitive that dictates the behavior of switch silicon. Its influence extends into the third layer of the OSI model. For standardized algorithmic transformations, these 48 bits are mathematically co-opted to generate global IPv6 addresses. Because modern infrastructure trusts this identifier implicitly, it serves as the front line and most frequent point of failure in network access control. To understand how traffic moves at the physical layer, we have to deconstruct the bit-level anatomy of the address, analyze how content-addressable memory executes these instructions, and diagnose the pathologies that cause Layer 2 fabrics to collapse. Treating the MAC address as a programmable logic gate is the prerequisite for securing modern network infrastructure. The MAC address is a 48-bit binary sequence, formatted as 6 hexadecimal pairs. To prevent local collisions, every address must be globally unique. The address is bifurcated. The first 24 bits form the Organizationally Unique Identifier. The final 24 bits serve as the NIC-specific extension. The IEEE centrally governs these OUIs. By assigning specific address blocks to hardware manufacturers, the OUI functions like a global area code, while the vendor manages the specific extension IDs for each unit they produce. Zooming into the first octet, these functional flags trigger specific hardware logic. The least significant bit in this octet is known as the IG bit. This bit defines the operational scope. A binary 0 indicates Unicast traffic targeted to one specific interface. A binary 1 indicates multicast traffic meant for a group. Immediately adjacent is the second least significant bit, the UL bit. This flag determines administrative authority. A 0 indicates a globally unique, factory-assigned identifier. A 1 designates a locally administered address. Administrators flip this bit to override the burned-in address, a technique used for specialized routing protocols or virtualization where MACs are predictably sequenced. To maintain order when localized overrides occur, the IEEE 802C standard defines specific quadrant patterns, preventing internal network collisions. These bits are hard-coded operational commands. They dictate how Layer 2 hardware handles a packet before the software layer even observes it. IPv6 presents a scale problem. Devices need to auto-configure 128-bit addresses natively without relying on a centralized DHCP server. The solution is stateless address auto-configuration, or SLAC. A device derives its global interface identifier directly from its local MAC address using the modified EUI 64 mechanism. This chart shows a hardware MAC address preparing for transformation. The first step splits the address exactly in half, separating the 24-bit OUI from the device ID. A 16-bit constant, represented as hex FFFE, is inserted into the center, bridging the two halves and expanding the total length to 64 bits. A final logic modification is required. The U/L bit, the 7th bit from the left, is inverted. Changing this 0 to a 1 shifts the identifier to a local IPv6 context. The modified EUI 64 identifier completes the SLAC process. While efficient, this broadcasts the hardware's persistent serial number across the global internet, embedding a trackable footprint into the device's public IP address. Through this algorithm, the local Layer 2 identifier is mathematically co-opted to enable Layer 3 routing. The physical ports on a switch are the points where these addresses dictate actual hardware behavior. A switch intelligently forwards Ethernet frames by basing its decisions entirely on an internal database of MAC addresses. When a frame enters an interface, the switch's forwarding logic executes a learning stage. It extracts the source MAC address from the frame header. The switch dynamically builds its Content-Addressable Memory, or CAM table, mapping the source MAC directly to the physical port. To prevent stale routing, the switch attaches an aging timer. If a device stops transmitting, the timer expires and the switch purges the mapping. Operating at line rate in an enterprise environment requires specialized hardware. Standard RAM searches sequentially, which introduces latency as address lists grow. Content-Addressable Memory works inversely. The switch inputs the MAC address, and the entire memory bank is searched simultaneously, returning the associated egress port in a single clock cycle. For more complex logic, like access control lists or quality of service tags, switches use Ternary CAM. TCAM processes don't care wildcard bits, matching network patterns instead of exact values. If a destination MAC address is not currently mapped in the CAM table, the switch relies on a fallback behavior. This is known as BUM traffic, broadcast, unknown unicast, and multicast frames. To guarantee the unknown unicast frame reaches its destination, the hardware floods copies out of every active port in the VLAN except the ingress interface. To sustain line rate forwarding across thousands of endpoints, network silicon relies on the bit-level predictability of these 48-bit strings. The rapid learning process that makes a switch efficient is simultaneously its most critical vulnerability. This diagram shows a condition called MAC flapping. It occurs when a switch receives frames sourced from the exact same MAC address on two distinct physical interfaces. When spanning tree protocols fail and create physical loops, or link aggregation partner keys are misconfigured, the hardware receives the same source MAC from multiple paths. The CAM table overwrites itself thousands of times a second. Return traffic is black-holed into the wrong ports, and CPU utilization spikes as the hardware struggles to stabilize its routing logic. Beyond configuration errors, the transmission of MAC addresses in plaintext on the local segment invites direct exploitation. Many environments use MAC address bypass to accommodate devices lacking advanced authentication, like printers or medical sensors. The switch is configured to permit network access purely based on a known MAC address. Because MAC spoofing is executed in software, an attacker can observe a printer's broadcast, clone that address, and instantly bypass network access controls. Network engineers mitigate this with port security policies, which restrict the number of learned MACs allowed per physical port. The mechanical simplicity that grants Layer 2 its speed relies on implicit trust. Without additional cryptographic layers, the fabric remains structurally vulnerable to anyone manipulating those 48 bits. We have traced the MAC address from a standardized prefix to an active flag that physically drives switching logic. The EUI format provides a flexible identifier that encapsulates across standard Ethernet, high-speed storage fabrics, and into automated IPv6 environments. Because the protocol operates on implicit hardware trust, security is never guaranteed out of the box. Any protocol at Layer 2 can be deceived by a spoofed identifier. Resolving network instability and locking down rogue devices requires administrators to trace logic flows directly through the MAC address tables. Maintaining infrastructure integrity requires a nuanced understanding of these 48 bits, from their standardized OUI origins to the way they physically drive the switching fabric.